Good, we're being recorded. All right, so hi everybody. Thanks for coming to my talk. So like Jim said, I am a rising fifth year. I work in particle phenomenology, and my advisor is Ben Safdie. So I guess I want to start, maybe it's a little bit obvious from my title, but by drawing a distinction between what I do and what people often think of as particle phenomenology. So I'm very much focused on searches for new physics that don't involve colliders. So nowhere here are we going to talk about colliders. Um, Almost all of my work is focused on cosmology and astrophysical indetection of dark matter, astrophysical indirect detection rather. But I also do a little bit of work on direct detection as well. It's very hands-off when it comes to colliders for me. Okay, so my talk is called Axion Cosmology and Detection. But to start off, I just wanted to go through sort of a crash course in particle physics history. And the reason that I want to do this is to sort of set the stage for why we do what we do, and also to argue that we've done a really good job in a really short amount of time before I admit some really embarrassing things about the state of the field. Okay, so the foundations of particle physics are found in this Greek philosophy of atomism, which comes about in about 400 BCE. And no one really makes progress on it until 1874. That's when Thomson discovers the electron. And it comes after that initial discovery that all of a sudden we start making lots and lots of progress. And it sort of culminates in the Bohr model of the atom. And this was a really cool theory. And the reason is it's a predictive mathematical framework that describes the interaction of particles, which really had not existed up until that point. Beginning in that 1913, people really start to think carefully about the way these particles behave, and all of a sudden we make lots and lots of progress. It's really this simple model that got us started. And since then, we've been able to come up with a number of predictive models. We've used them to identify technical problems. Those have led to the development of new theories and bigger experiments. Those experiments were overwhelmingly successful for about 100 years. Basically, from the early 1900s until 2012, theory and experiment keep pace with each other. Discoveries get made that inform one another. And in 2012, this culminates in the discovery of the Higgs boson. And at the time that we discover the Higgs boson, which is the explanation we have for why particles have masses, or why the particles we know have masses, we felt that the standard model was complete. And you can tell how complete we felt it was based on we made this very nice diagram, which doesn't have room for anything else in it. So we have this exceptionally well-tested theory of particle interactions that involve quarks and leptons, neutrinos, gauge bosons that mediate forces, and at the center of it all, the Higgs boson. And this is really one of the most remarkably well-tested, probably the most well-tested theory in science. So the G-2 experiment has verified standard model prediction to something like 10 significant digits. It's really quite incredible how well the standard model describes the physics that we are able to observe. Okay, but that's a real qualification, because although it describes everything we've been able to create or detect on Earth, you could ask, does the standard model actually describe our universe? So the first hint that it might not, what comes from rotation curves. So what are rotation curves? You basically go out, you look at the stars, and you ask how fast are they moving as a function of their distance from the galactic center. This could be the Milky Way galaxy, but this has also been measured for many, many other galaxies. So it turns out, can you all see my mouse? I'm going to need somebody to unmute.
Yeah, we can see it.
Excellent, thank you. All right, so if you wanted to do a sort of self-consistent prediction of what you thought the rotation curves would be, you'd go out, you'd survey all of the mass, and then you'd ask, how is that mass moving? So if you survey the mass and you come up with a prediction for those rotation curves, you get this dashed black or dashed gray line. So what this predicts is that things that are in the Milky Way have velocities that peak around roughly 60 kilometers per second. These happen about 10,000 light years away from the galactic center. And after that, we would expect the rotational velocities of things within the galaxy to start falling off, like this tail. On the other hand, that's exactly not what we see. So, I mean, there's more data points, but like the first order thing is the sun is moving in the galactic frame at about a velocity of 250 kilometers per second, which doesn't fit anywhere in on that dashed gray line. So you should be worried about that, because that means either your predictions for the rotation curves are totally wrong, or it means that you think the sun is going to someday escape the Milky Way galaxy. Both of those don't really make sense. What this leads us to infer is that there's actually lots and lots of matter that's inside the galaxy, and we just weren't able to identify it. So that's a pretty vanilla explanation for things. And this gets, so what we're able to do then is make predictions for what that mass distribution is based on the stellar rotational velocities. Based on that inferred mass distribution, you can make predictions for other rotational velocities beyond where you expect to see stars. And we follow up those with observations of the 21 centimeter hydrogen line. And it turns out that the 21 centimeter hydrogen line, which is going to get redshifted based on rotational velocities, that gets redshifted in a way that's consistent with the mass distribution that we inferred from the rotational motion of the stars. So this seems to be a pretty consistent story then, that there's all this matter inside of the galaxy that we just weren't able to find. Okay. But we can also evidence this with not these cosmological, or rather, not these astrophysical measurements, but instead some cosmological measurements. So these measurements basically have to do with looking at what the cosmic microwave background looks like at its present day. So the cosmic microwave background is light that's left over from when the universe was about 380,000 years old. It's our best probe of the universe at its earliest state. It's actually quite hard to figure out anything that's going on before the cosmic microwave background gets produced. Now, if you look at the cosmic microwave background, the observations of the cosmic microwave background are only compatible with theory if you have about the measurements of the cosmic microwave background are only compatible with theory predictions if you have about 5 or 6 times as much matter in the universe as you thought you did. So that actually hangs together with our observation that there was a lot of mass left in these galaxies that we hadn't been able to identify. Now, it's pretty easy to think that maybe the mass we identified was standard model matter, and we just weren't able to see it for whatever reason. But the standard model is actually such a good and predictive theory that we're able to infer cosmological abundances of standard model matter based on its thermal history in the universe. And we know that the amount of standard model matter in the universe is not compatible with the amount of matter that we need in the universe. So this leads us to infer that about 5 times as much matter in the universe as standard model matter is as of yet unidentified. So this is a plot from the Planck mission, which is a CMB observation that inferred these matter fractions. So we see only 5% of the energy density of the universe is in the standard model, which is kind of shocking that we were able to make such a good theory and not describe 95% of the things in the universe. Now, the majority of the energy density in the universe is actually dark energy, but we're so clueless about what dark energy is or isn't that we're not even going to talk about it, really. It's not a question that we can reasonably probe right now. Dark matter, on the other hand, so this other stuff, other matter that's in the universe that behaves just like the matter that we know exists in the standard model, except it isn't in the standard model, that's a more reasonable target for us to go after. We have theory frameworks that describe the way matter behaves, and the goal might be to just extend the standard model to add new degrees of freedom to it, such that it includes the whatever that dark matter might be. But if we're going to do that, we need to detect it. We need to infer its particle physics properties, because right now all we have is evidence of its gravitational interactions. That's what these CMB and galaxy rotation curves are really telling you. It's just saying that dark matter was there, its gravity mattered at early times in the universe, and its gravity matters today. Okay, so when it comes to writing down theories for what dark matter is, that's also compatible with the standard model, we're really good at that. We're really good at writing down theories. So this is sort of the intimidation form of the dark matter model landscape. So there are things on here like that it might be coming from X dimensions. It might be dark matter might have its origin in supersymmetry. There are models of asymmetric dark matter, which are related to dark photons. Warm dark matter, which are closely related to this idea that there might be heavy sterile neutrinos. There's a lot to look at. And it's hard to figure out, if you just look at this plot, where do I look? There's more ideas than really can be tested right now. So what I want to do is I want to focus on this circle, which is axion-like particles and the way that it overlaps with QCD axions and axion dark matter. And I want to explain like how we navigate this complicated model space when we decide what experiments to build and what observations to go out and do, and why I think axions and axion-like particles are a really good target. Okay, so in particular, my guiding principle here is going to be to try to kill two birds with one stone. It felt a little shameless to include this graphic here, but I was mostly entertained that Forbes, which is a very valuable company, actually ran this image too. So if it's good enough for them, it's good enough for me. On the other hand, PETA, who really has their finger on the pulse of what matters right now, is encouraging us to avoid speciesist language and to say, feed two birds with one stone. But moving on. So I want to solve two problems at once with my dark matter. And the rationale here is essentially, the standard model is a really good theory. It works so well, it's sort of surprising to think that there might be lots and lots of problems, all with an independent origin. So instead, you might expect that whatever we don't know about might solve more than one existing problem. So one of our existing problems is, what is the dark matter? But another really compelling existing problem is essentially, why is the neutron electric dipole moment so small? And if you wanted to ask this in the context of quantum field theory, if you looked at the low energy QCD Lagrangian, it's totally fair for the QCD Lagrangian to have a term that looks like this. So if you're familiar with what a normal gauge coupling term looks like, it looks like GG, G mu nu, G mu nu. So here I've written it, there's a typo. Well, here I've written it with the antisymmetric tensor contracting those two gauge fields. This is a totally fair term to include in low energy QCD Lagrangian. It would come with some coupling strength theta bar. And it turns out that that theta bar term is related to a phase of an angle. And you could ask, well, what values can a phase of an angle take? Just 0 to 2 pi. So that's fine. And then you would ask, what value does theta bar take in nature? And to the best of our ability to tell, it's 0. It's measured to be 0 up to 1 part in 10 to the 10. So that's really precise. And it raises questions. Why is this parameter that could have been anything so close to 0? And oftentimes, particle physicists like to come up with anthropic reasons that parameters take particular values, right? This idea that if the Higgs coupling to matter was a little different, it would have never supported life. But as far as we can tell, the value of this theta bar term has essentially no effect on the present day state of the universe. Almost all of what it does is contribute to a neutron electric dipole moment, which has almost no observational consequences. The reason we haven't measured the neutron electric dipole moment better is because if it was present, the effect would be so weak that it would be hard to see it anyway. Okay, so this is a problem. Why is this parameter small? And we're going to solve it with the introduction of an axion. So we introduce the axion, and that name actually comes from a brand of dish detergent. The idea is that you're cleaning up your messes. So what you do with the axion is you originally had this theta bar GG dual term. And now what you do is you add the axion, which is this field that acts as a dynamical degree of freedom. And then if you look at what the vacuum energy of QCD looks like, it turns out it has a potential that looks something like this 1 minus cosine potential. Now the QCD vacuum energy wants to zero out the vacuum. The QCD vacuum wants to zero out the vacuum energy just to descend to the lowest energy state. So what the axion does is it actually goes to the value of theta bar, and it makes it look like theta bar is effectively zero. If you redefine some effective theta bar, which is the real theta bar parameter of your theory minus that axion. And in that way, it sort of dynamically solves our problem, and we can avoid doing some sort of fine-tuning. And this idea was actually so compelling that, or rather, the problem was so pressing, and this idea was so compelling that the people who originally wrote down the model didn't even realize that axions, this new particle that they were introducing, could also be the dark matter. It's Pesce and Quinn come up with this idea, but it's not for about a year or two until Weinberg and Wilczek point out that it's a new degree of freedom that could certainly be the dark matter. So this is great. This is one solution for two problems. Now we just have to go out and look for it. So how do we look for it? Essentially, axions have an interaction with photons. You can tune this to be small, but it's sort of a generic property. So that's actually great because we're really good at detecting photons. The downside is that the mixing of axion with these photons has to be very, very weak. Otherwise, the dark matter isn't really dark after all. So we're looking for this new degree of freedom. It's going to be weakly coupled to photons, and that's going to give us an avenue to pursue. So if you write down, or rather, if you make a plot of what you think the axion parameter space is, so the full range of what you think are possible axion masses on the x-axis, and then the range of allowable axion couplings in the y-axis, the best motivated models are these models like KSVZ, some initialism of the 4 people that invented it, same with DFSZ. They live down here, these 2 solid lines and this yellow band around it. Now, all of these are different experimental and observational probes that we've used to constrain axions thus far. And you can see that we're doing a really bad job. Almost all of the motivated parameter space is wide open, which means that we have a lot of work to do. And really the reason that the state of things is such that it is for something like 50 years, everybody was so confident that dark matter was going to be weakly interacting massive particles that were associated with supersymmetry that they didn't really bother looking for axions. Really, the only people that were looking carefully and have been for a long time is the ADMX collaboration right here. We'll talk about that a little more. Okay, but before I get into talking about experimental searches for axions, I want to talk about their somewhat unique cosmology. And their cosmology and their thermal history is interesting in that axions are a non-thermal relic. So most of the particles that we think about and we know, they're just left over. There was some high temperature plasma in the early universe, and it cooled down, and the particles that we have are just the things that are left over after it cooled down. Axions don't get produced like that. They are produced by a non-thermal mechanism, and it leads to some interesting effects. So if I wanted to really look at what the thermal history of the axion is, I need to write down some effective theory. So apologies for that, this is a little technical. So I write this theory down, and I write it down as a complex scalar. So that's this complex scalar phi term. And this is the Lagrangian for your theory. So if I can break this down into a few things. So first off, there's just the kinetic term for this complex scalar. I'm going to call that the PQ field. And that's just saying the PQ field is a wave, and it's wiggling. Now, on top of that, the PQ field can interact with itself. So it looks like this. There's a quartic coupling, phi squared minus fa squared squared. And there's also a thermal mass, which just says the PQ field from its interactions with the plasma acquires a mass. And it's not important how, we're just going to put it in as an effective mass. And you can see that effective mass is temperature dependent. That's the T here. So as the temperature drops, its effective mass drops out. Now on top of this, so in this complex scalar, there's two components, basically an x component and a y component. And it turns out there's a contribution to the potential. We looked at this a little bit before, but it depends on the cosine of the argument of that complex scalar, or basically where on the circle that complex scalar is pointing. That phase is actually what's going to become our axion. Now what happens is eventually the thermal mass drops out. You have a spontaneous symmetry breaking where the magnitude, so the radius on the circle where that complex scalar is living, gets frozen in. But the phase is still a dynamical degree of freedom, right? You can spin things around in a circle without changing the radius. So that's how we have a spontaneous symmetry breaking that gets rid of one of the degrees of freedom, that radial mode. But it leaves us with the angular mode, which is, again, our axion. So this axion, it has a mass. We need it to have a mass, otherwise it's not going to be a good dark matter candidate. And it's actually going to pick up its mass from QCD effects. And that has some complicated time dependence that we're just going to parameterize by MAT. Okay, so this story here is that the universe is initially at a very high temperature. The temperature descends, and we get our axion produced. Now, when that axion gets produced in a spontaneous symmetry breaking, we're again thinking about where the field is living on the circle. And there's nothing special about any place on the circle. So the field just picks out a random value. It has that random value as an initial condition, and it evolves in some way to its present day state. Now there's two possibilities. It could be that this axion field gets produced before inflation. And what happens then is there's one value of the axion field inside this, what is the causal horizon before inflation. And then inflation blows up everything. So now it looks like everywhere is just taking that value theta naught. I mean, there could have been theta 1, theta 2, theta 3 out here, but we never would have seen them because inflation moved them too far away. In that case, it's really easy to predict the axion abundance as a function of that initial angle theta. It looks something like the mass of the axion squared times that initial angle squared. But this is a little non-predictive because, like I've been telling you, there's nothing special about any place on the circle, which means that you're just doing a uniform draw on 0 to 2 pi. You get what you get, and then it evolves to the present day state. But really small numbers and numbers really close to 2 pi are totally allowed, which means that there's like orders of magnitude of statistical uncertainty in what the axion abundance would be today. So it's sort of, you can really just treat it like a free parameter, and you should go out and look for it. But it's hard to make predictive statements about this sort of scenario. Now, there's a much more interesting and more predictive scenario, which is the one where the spontaneous symmetry breaking, happens after inflation. And then when that happens, inflation's happened, so we're in our little inflated patch. And now the PQ symmetry breaking happens, and on lots of little different places, you get different values of theta. It turns out there would be something like 10 to the 49 different samplings of theta in the observable universe today. And that's great because I don't know how to characterize, I can't make a good prediction for what a single draw from 0 to 2 pi is going to be. But I can make a really good prediction about what 10 to the 49 draws from 0 to 2 pi averaged together are going to look like. So now the theta ensemble is statistically characterized, and this is a totally predictive theory, which is really cool. So that's the scenario I'm going to focus on. And it's especially interesting because something I said should have set off alarm bells, which is that theta is taking all these independent values on little different patches of the universe. I mean, those patches have to hit one another, and something violent is going to happen when you have a patch at theta 1 and a patch at theta 2. So if you really want to understand the way you would evolve this ensemble to its present day, which has it has about 13 billion years to do that, you need to do some hard calculations. So I've been telling you a detailed story, and really what's going on here is the initial conditions are complicated, the evolution is nonlinear, and there's an enormous dynamical range, because again, 13 billion years. It's not really a pencil and paper calculationally tractable problem. So we have to do simulation. And that's something we've been doing in my group. So myself and some of my collaborators worked very hard to put together a simulation to see what the axion field would look like at times shortly after the QCD phase transition, when the axion picks up its mass and really starts to behave like cold dark matter. I'm going to play that animation now. So what this animation is doing, bright spots are high density regions, dark spots are low density regions. And there's some complicated interactions of topological structures that are called strings and other topological structures that are called domains, or domain walls rather. And really this is just saying nonlinear effects are important, so you have to do a really detailed simulation. And at the end of our simulation, you see something like this. So there's these bright spots of high density regions, so lots of axions are there. And then there's these dark spots where there aren't lots of axions. So there's a lot of granularity to the distribution of axions at the time that they start behaving like dark matter, like matter. Now, this was a totally field theory simulation in that there's no gravity. But of course, we know that gravity is an important force. We see it every day. And also, this key detail, the reason that we know about dark matter in the first place is because we saw its gravitational effects. We know it's interacting gravitationally. So what we have to do is we have to take this initial condition now, after the end of the simulation, this distribution of axion dark matter, and we have to run it through gravitational n-body simulations. So what we do is we take that distribution, we place down lots of little particles, and we let them evolve under each other's gravity. So this is an animation from my group, where you can see the particles starting to clump up into structures that we call halos. Now you could ask, how can you characterize the distribution of halos? And another group has worked on that, and they have this distribution of halo masses, which say something to the effect of, you should be seeing lots of little axion clumps that are something like 10 to the 15 solar masses. So to try to provide some scale, the Earth is about 10 to the minus 6 solar masses. I believe the moon is like 10 to the minus 9. So these are really tiny on sort of astrophysical mass scales. But it matters because it means that the dark matter could be clumped up today. And that's really different from normal WIMP dark matter scenarios where people are really just thinking about free-floating particles just whizzing around the galaxy. Now we have to worry that our particles are clumped and the clumps are interacting with one another. And it's sort of a challenging question for dark matter direct detection. The idea of how do you decide where to look changes when your dark matter is diffuse or clumped or so on. So that's why we're really interested in this axion cosmology in the first place. If we want to go out and look for axions, we need to understand their cosmology and the structures they form to come up with good strategies. And I guess I also wanted to clarify, I think there's this language around halos that's a little bit opaque sometimes, but a halo is really just a gravitationally collapsed structure. So there's like the Milky Way, there's a Milky Way halo, and then the Milky Way galaxy, which is the baryonic matter, is sitting inside the Milky Way halo. It's not a really special or technical term. It's just one everybody uses and never explains. So yeah, the story here is that there are these little halos that are now 10 to the minus 27 times lighter, or 10 to the 27 times lighter than the Milky Way. And that's what's the dark matter in the Milky Way. Okay, so the first strategy that people really use to go look for axions is direct detection. So I wanted to give a brief overview of direct detection efforts. So again, we're looking for this coupling with photons. And if I wanted to write it down, not in terms of like gauge field, like GG dual or something, right? But I just want to write it down now in terms of like an electric field and a magnetic field that I know and I understand. It looks something like this. There's this axion term, and it multiplies the dot product of the electric field and the magnetic field, and that interaction strength is going to get set by this coupling GA gamma gamma. That's what we were looking at in that constraint plot. So when you're coming up with a strategy, you're going to want to make one of the, GA gamma gamma is going to be small. These are weakly interacting. So you're also stuck with whatever A you have where you're looking. The only thing you can really control is the size of these electromagnetic fields. Now, if you go and ask how big are the biggest electric fields that we generate in natural units, which make comparison easy, and you compare them to the size of the biggest magnetic fields that we can generate, and you again compare them in natural units, you'll find that it's actually a lot easier to generate big magnetic fields than it is to generate big electric fields, which is why almost all of the direct detection experiments are focused on generating large background magnetic fields for ambient axions to interact with. So for a long time, the only real precision experiments in the sort of axion world were cavity experiments. So what do cavity experiments do? So a cavity experiment looks something like this. I've never been able to find a good picture of a cavity experiment. They're always a terrible aspect ratio and are just a block of metal. But it's what we have to work with. So this is actually the Axion dark matter experiment. It's located at the University of Washington, and this is the experiment that's contributing to the bounds that are cutting all the way down here, getting into the motivated region of the parameter space. So the way these cavity experiments work is you make a big cavity, you put a big magnetic field inside the cavity, and you wait for axions to come in and to convert to photons. Now it turns out, just due to the energetics, those axions that come in and convert are going to produce microwave radiation. And you go out and you look for the microwave radiation, or in the case of every experiment so far, you don't see any microwave radiation. So instead of saying, I've discovered the axion, you say, I've ruled out an axion with this coupling strength and this mass, otherwise I would have seen it in my cavity. So that's how we get to all of these limits. Cavity experiments are hard, and they're slow. ADMX has been running for like 20 years, and this is where they're at. There's some new experiments. One's CAP, which is out in Korea, and Haystack. Haystack comes about from an internal schism in the ADMX collaboration, and people split off and went to go look at higher mass axions. But progress is slow, and they're also not covering all of this space and all of this space, which are regions that are just as motivated, if not more, than the ones that the cavities are looking at. Okay, so I wanted to talk. Oh, wow, that's embarrassing. This is an experiment I work on, and I spelled the name wrong. So the name of the experiment is Abracadabra, not Abracada. So I can tell you what Abracadabra stands for. It's a broadband resonant approach to cosmic axion detection with an amplifying B-field ring apparatus. So the story here is just that the axion is going to behave like a wave. So this is sort of the wave equation for axions. So you see this cosine, and the oscillation speed is set by the axion mass. Now, it turns out that an oscillating magnetic field, or rather an oscillating axion field, when it interacts with a background magnetic field, will produce an oscillating magnetic field. So that gives us a really clean target. We just go out and we look for an oscillating magnetic field. So what's so exciting about this actually is that there's a prototype of this experiment that's been built. They've collected data. There's been a first run of results, and unfortunately, due to some instrumentation error, the constraints don't live on this plot. On the other hand, they've done a second round of data, and I can tell you that the results are good because I'm the one who analyzed it. And the constraints are living somewhere like here, which is starting to cut into unprobed parameter space. Now this looks really modest because again, I've pointed out this motivated region of the axion parameter space, and we're going to get there. So this prototype is really tiny. Your detection sensitivity scales like the square root of your volume, and it scales like the square root of your B field. Now, our detector it's called Abra 10 centimeter, so of course it's 12 centimeters wide and tall. But the plans for this future Abra QCD detector are to build a detector that is something like 16 meters tall and 18 meters wide. And instead of having a 1 Tesla magnetic field, to have a 10 Tesla magnetic field. Really, right now we're at the stage of demonstrating a working technology, and it works, which is exciting. Now we just need somebody to give us $10 to $20 million so we can build this one. Of course, we have proposed some staged advances towards that largest scale detector. Okay, so there's another idea for a detection scheme. Oh, rather, I should say also, so I was showing you these cavity constraints that are over here, and Abracadabra is aimed at getting to like nano EV scale axions and even smaller. So you see, this is living over here. That's the region that we want to probe. Another experiment that is targeting this low energy axion parameter space, or low mass axion parameter space, is the Casper experiment. And the Casper experiment is actually really cool because unlike all of the experiments I've told you so far, it does not depend on the axion coupling to photons. It depends on the axion coupling to nucleons. So the story here is that you set up a bunch of neutrons, and now you have an axion field, and the axion field is oscillating, and you set up a background magnetic field. So now your oscillating axion field and your background magnetic field produce an oscillating magnetic field. And that oscillating magnetic field torques the neutrons that you've set up, and it produces an observable nuclear magnetic resonance effect. So this is really cool. And one of the reasons people are so excited about this is actually that the coupling of axions to nucleons is a little more natural and generic than the coupling to photons. So it's a really neat idea. On the other hand, it's at very early stages, and it's an extremely ambitious proposal. I have heard people jokingly say that the path to Casper phase 3, with its constraints indicated here, is about 2 to 3 Nobel Prizes. So we might not get everything we're told we're going to get from Casper, but it's still a very cool idea and one that a lot of people are excited about. So I told you about modeling structure before. We did these field simulations, and we did these gravitational simulations, and we saw these clumps of dark matter. And I don't want to get into too much detail, but it's important for direct detection experiments because they tell you what the signal shape should look like. So if you were really naive about what your signal would look like, you would think it would just look like this in terms of frequency. You would take some data, you'd look at it in the frequency domain, and it would look like a bump. And you'd look for that bump. And that's something you can do, it's fine. But if you correctly accommodate information about axion structure, like these little clumps flying around, you might have much more drastic time-varying signals that would manifest in your detector, something like this animation here. If you didn't know to look for it, you might miss it. And that would be a real shame if we just didn't know what the signal was supposed to look like in the first place, and we ruled out an axion that was actually there in the first. We don't want to do that, so that's why this cosmology story matters a lot for us. Okay, so I just wanted to give like a critical overview of these direct detection ideas. Again, you're waiting for axions to just fly through and do something with photons. You need a big magnetic field, which is still hard to do. And also, one thing that's unfortunate is most of the dark matter is at the galactic center. It's not here. So you're stuck on Earth, which is a shame, because there are much better places to look in a direct detection experiment. So it begs the question, is this like really an optimal or complete strategy? And my argument is that no, it's at least not complete, And the thing that you should also be doing is indirect detection. So what indirect detection just means we're going to use astrophysical and cosmological measurements to infer the presence or absence of axions. And I wanted to tell you about a specific example of indirect detection efforts that I'm working on. So it turns out that neutron stars are really good laboratories, actually, for axions. So why? First, neutron stars have huge magnetic fields. The biggest magnetic fields that we can produce on Earth are something like 30 Tesla. The biggest magnetic fields at neutron stars are something like 10 to the 15 Tesla. So because the axion interactions are going to scale with the magnetic field, you're picking up a huge boost in signal strength. Neutron stars are actually really big, and they're not big compared to Earth. They have a radius about 10 kilometers, but they are really big compared to direct detection laboratories, which means that in addition to having really big fields, they're also just seeing lots of axions. On top of that, there are a lot of neutron stars that are near the galactic center, which means that they're located in places where we expect the axion density to be quite high. So all of these are things that boost your signal. You, of course, would lose on the signal because the neutron stars are very far away, but you can still win. You just need to know what signal to look for. On top of all of this, we know the Milky Way density reasonably well. And if what I'm saying is true about the sort of granularity of axions, you might worry that there just aren't axions here because it happened that we weren't co-located with a clump. But we know on average what the Milky Way density is, Milky Way dark matter density is. And there's lots of different neutron stars. So even if the axions are sort of clumped up, we're likely to have a neutron star that's co-located with a clump of axions. So this gets around this possibility that we weren't even going to see axions in the first place with our direct detection. Okay, so what's the particular scheme? So let me detail the neutron star for you. A neutron star, to sort of first approximation, it's a ball, it's rotating, and it also has a magnetic dipole, which is sourcing those very large fields. Now, the rotational axis and the magnetic dipole don't have to be totally aligned, but typically they're very close to aligned. So we get these strong dipole magnetic fields, and there's these radiation jets that are actually how we detect many neutron stars. We call these pulsars. And the story here is that infalling axion dark matter is going to encounter these strong magnetic fields, and it's going to convert. It's going to convert to photons. These photons turn out to be radio photons, and these radio photons can then make their way to Earth, and we can try to go look for them. When we do that, we should use the tools that we use to look for radio emission, just radio telescopes. And it turns out that you would expect to see a signal which looks something like this bump plotted in radio frequency and radio power. Now, the shape of the bump is going to depend on certain things like your neutron star modeling and the axion mass and so on, but that there is a bump and we can go look for it, is going to stay true the whole time. So that's what we're going to do. We're going to point radio telescopes at neutron stars or at places we expect to be dense in neutron stars, and we're going to try to detect axions or rule them out in the regions that we're sensitive to. Of course, this analysis is hard because radio data is complicated and our signal is really messy and has lots of stochasticity because we don't know about all of the neutron stars in the galaxy. We just have to model them with populations. But where are we going? We're going somewhere like this. So again, these are our normal axion cavity experiment constraints. And most optimistically, with futuristic telescopes, we could do something that would do as good as the cavity experiments are projected to do, and would cover a wider range of parameter space in terms of the axion mass. Now, you should note that there are 2 decades of axion masses plotted here. And I wanted to set the scale so I can show you what we've actually gotten done. Also note that these lines are living around like 10 to the minus 16 for the axion-photon coupling, because all we've done so far is this. So what we did is we got an hour of telescope time on the Green Bank telescope. That was the one that was shown at the beginning of my slides, and another hour of time at the Effelsberg radio telescope. We took data at frequencies between 1 and 3 gigahertz, and we used it to place some pretty modest constraints on the axion parameter space. We're still proud of these. They're ruling out previously unprobed regions of the parameter space, but there's a lot of work to be done to actually get to where we think our projected sensitivity is. Mostly, we need more observation time. Okay, so one of the reasons that we want more observation time is because radio data is really messy. So I can tell you that you pick up local radio stations. For not with these radio telescopes, there are no radio stations around, but actually abracadabra, this experiment, it picks up local radio stations that happen to be sitting in the same axion frequency range. There's all sorts of stuff that just happens. And if you look at if this is one frequency that we fixed out of our data, plotted over 30 minutes of collection time, and you see that there's crazy things going on. And we have to veto those, but it leads to less exposure than we would have expected, which leads to less strong constraints. So we need more time. We also just need better telescopes. So the telescopes that we used are these big single dish telescopes, which aren't totally optimal. What we're excited for in the future is the square kilometer array, which will be a square kilometer of small telescopes, uniformly spaced. And what those small telescopes will do is have, one, a much larger effective collecting area, and two, will allow for spatial resolution. So not just seeing whatever's in the beam, but you can actually figure out where exactly on the sky it is. And that tells you some useful information that you can use to set even stronger constraints. There's also a lot of modeling to be done on the neutron star side of things. So this might be done through magnetohydrodynamic simulations, but the idea is just that there are really complicated neutron stars that have even larger magnetic fields that we know about. So one, for example, is the galactic center magnetar. So this is also great because it sees lots of axions because it's in such a dense region. But the problem is we know that the galactic center magnetar is qualitatively different than the neutron stars that we know how to model. So we haven't included it in our analysis, but in the future, with a better understanding of these classes of neutron stars, we'll have better observational targets that we can use to set better constraints. So I just wanted to show this and recap that the parameter space is wide open and we're working hard, but there are probably decades of effort before we can really say anything about really whether the axion is living in this well-motivated region of parameter space or not. Do I end at 12:50 or 1?
We still have Q&A after this. So
okay.
If you want to leave like a few minutes for a Q&A.
Yeah, okay. Briefly, I guess I wanted to do something informal, which was just to sort of assess something that maybe many of you have heard about. So recently, about a week ago, the Xenon 1-ton collaboration announced a 3.5 sigma excess that's consistent with a solar axion, which is to say an axion that gets produced in the thermal bath of the sun and makes its way to Earth and then slams into one of the xenon atoms, rather one of the electrons that's in this big xenon bath that they keep, leading to some detected recoil events. So that sounds very exciting, 3.5 sigma. There are a lot of reasons to be very cautious about this result. So what I'm showing here is their data. This is straight from their paper. And one of the things that just this is on my mind because we're working on it right now. Their background model is shown in gray, and their fit to the signal model, signal plus background, is shown in red. Turns out this is 3.5 sigma, but it is concerning to see some of these large residuals of the data around the background model. And there's a lot of reasons to be concerned that they're not actually describing the background as well as they think they do. There's another reason to be very concerned, which is that this is their results, which depend on the axion coupling to electrons plotted in the mass coupling parameter space. And their results are this black line. So they're setting limits at high masses. And then here, this blue line, this is what they're saying. This basically corresponds to their detection. It turns out their detection is already ruled out by cooling bounds. So what happens is if you have an axion, then it's an additional degree of freedom by which white dwarfs and red giants can dissipate energy. And that means they don't live as long. But we actually go out and we measure, this is not work I do, not the royal we. We go out and we measure the populations of white dwarfs, and it turns out they're very consistent with theoretical expectations, which lets us set a tight bound on axioms, and one that nominally rules out the coupling strength required to produce the xenon one-ton excess. There are a lot of reasons to be skeptical, but there's a lot of reasons to also still be excited. It's fun whenever there's any sort of detected excess, and there's been a lot of theory work done recently trying to understand what might be giving you that excess in the first place. Okay, I'm going to skip over these slides and I can take questions. And I just want to thank everybody for listening. I wanted to do one of these PGSSs for a really long time, and it wasn't quite optimal circumstances, but I'm glad I got to do one.
Thank you. Anybody have questions? You can unmute yourself.
I have a question, Josh. So you mentioned that there is some tension between the axioelectric coupling from stellar cooling bounds and the xenon one-ton result.
Yeah.
But there's also, if you look at the axion photon coupling versus axioelectric coupling space, you can see that the inclusion bounds for xenon one-ton and stellar cooling are also in tension. So my question is, are there theoretical reasons or like theoretical correlations between the two different axion couplings?
Yeah. So in the xenon experiment, you're looking at electron recoil events. So if you're looking for an axion, you have to have an electron coupling, right? So when you want to introduce another coupling, maybe the coupling to nucleons, the coupling to photons or something like this, you're bringing that in because you have different ways of producing the axion in the sun. But this critical feature is the axion-electron coupling. Otherwise, you never see it in xenon. So I think that the sharpest thing to do is to just look at what electron coupling they need to see anything in the first place and see that it is ruled out at like 10 sigma by these white dwarf cooling bounds, and say, well, I'm not too worried about what you have to say about GA gamma gamma or GANN because you had to have that GAEE and you can't. I mean, okay, so I'm expressing a position that is very trusting of the white dwarf and red giant cooling bounds, but I think those limits tend to be well trusted. So.
Thanks.
How will direct detection and indirect detection compare, like once you have sort of the next generation of experiment, like with this square kilometer array, and then also with like a much larger cavity? Like, is one going to dominate, or are they just in different regions of the parameter space?
Let me go back to my slides for that. Okay, so here's this comparison of limits, or projected limits really, because okay, this solid thing is the real limits, this semi-transparent thing is the projected limits, and this is projected limits from radio. So cavities don't get bigger. Basically, you need to tune the size of your cavity to the wavelength of the axion that you're looking for. So you're a bit stuck there. They're not going to get bigger. They might get better magnetic fields. They might also just build more of them. So there are improvements that can be made, but those are sort of costly experiment paradigm changing improvements. I would say that there's a similar story for the square kilometer array, which is that it hasn't been built yet, And there are a few different proposals, and it's not clear if these are proposals for the most optimistic version of square kilometer array. But I would say that there are theory improvements that can be made that would strengthen the radial limits. And the radial limits on their own would cover a much larger range of the masses that you're interested in looking for. On the other hand, there are large systematic uncertainties with indirect detection. And in some sense, the radio searches are more of a discovery tool than they are an actual limit setting tool. So I think there's a lot of reasons to do them in tandem. But the radio situation, the radio search really does help you avoid this possibility of axion clumps just aren't around Earth, so the direct detection experiments would have never seen them.
Hey, Josh. You talked about how this axion phase angle settling in many different values could create like this cosmic string network.
Yep.
Could we see that at all in any CMB measurements? And can you talk about that?
No. So unfortunately, you can't. So the reason is these strings get formed when the axion acquires its mass during the QCD phase transition. The QCD phase transition happens before the CMB gets produced. So what you would be hoping for is that these strings last long enough to be around still when the CMB gets produced, but they don't. So it's hard to you wouldn't be able to say anything, at least for the class of axion models that we're looking for. There are other models where you endow the axion potential with additional properties such that the domain walls and the strings are long-lived. But those are then hard to reconcile with the expansion history of the universe. So it's sort of a tight squeeze. And to the best of my knowledge, there aren't really compelling directions to make that sort of probe.
All right, anyone else? Last question? Okay, if there's none, thank you very much for coming and listening to Josh's presentation. And I just want to remind people to please sign in and give Josh feedback. And once again, thank you. Thank you very much.